Good afternoon and welcome to our second webinar in the series SIPROTEC 5 Motor Protection. Last week, we had the live stream session for Motor Protection Basics with many hundreds of participants, and we were happy to welcome people from all over Europe and in fact from across the globe. That showed us how interesting the topic can be for those engineers with these needs. Today, we will address issues in more detail. The advanced motor protection will cover engineering, parameterization, configuration, and commissioning issues. My name is Edward Strasser, head of the Channel Partner Program in Siemens Electrification Automation for the 26 countries, all managed from Siemens Austria. I'm happy to be your moderator for this event today, and it offers valuable information both for operations and maintenance engineers, as well as design and protection engineers, and any preparing technical specifications for projects requiring motor protection. Our expert today in today's webinar is Klaus Wagner. He's a specialist for motor protection for over 25 years of protection experience with SIPROTEC in various protection technologies here at Siemens. I mentioned channel partners earlier, and by this I mean integrators, EPCs, switchgear manufacturers, similar companies who use the product portfolio of Siemens Electrification Automation in their own customer projects. If your company meets this kind of description and you're not yet a partner of ours, talk to your local Siemens representatives about the possibility of joining our VAR Grid Plus partner program. A few words about today's program. We will break the session into 3 blocks of information, about 30 minutes each, stopping to answer a few questions each time before we move on, with a total duration of about 1 hour and 45 minutes. In terms of quality of the webinar, when we rehearsed for this event, we also recorded, and we found that the quality of many parts was so good, we wanted to share them with you in the top quality to make sure everything was clear and worked well. But during that time, we will be here in the studio with you, addressing the questions you have and answering some of them right in the chat. So finally, I'd like to mention to you, in the upper right-hand corner of your screen, you will see a zone where you can participate in chat about the subject, put some questions in, and later on you will also see a zone there for downloading some documents near the end of today's webinar. So Klaus, would you like to take over?
Yes, thanks Edward for the introduction. Only a few words. Our webinar basically is split into 3 parts. Logically split into 3 parts. I will give you a very short overview of our protection relays that are fit for motor protection. Then I will present you a setting example, so motor data, and then discussing the settings for this motor data. And at the end, we have some nice additional tools to work with SIPROTEC 5. I will explain some of these tools. Some of these tools I already explained in detail in the first webinar, so I split that up, and the others now will be explained in this webinar. Okay, I would say, let's start.
Okay, let's go. Thank you, Klaus.
So, welcome to our SIPROTEC 5 Motor Protection Advanced Training. Here we go a little bit more into detail. Especially, I thought I explain you a setting example, whereas for the introduction and overview of our SIPROTEC 5 relays, we have another webinar which took already place. So if you want to listen to this, have a look there. Okay. A short overview of what we have as motor protection relays and how to use them. This is more kind of rough guideline than a very strict rule, because it depends on the situation, on the philosophy. Basically, we subdivided the motors to small, medium and large motors, not so much on the power, depending on the power of the motor, but on the application of protection functions, which we typically find for the smaller and bigger motors. So for the small motors, typically with just one current transformer, and preferably we can use here the 7SX800, the 7SK82 or the 7SX82, or optionally our modular devices, which is the 7SK85 or the 7SX85. Maybe quickly some words about the naming. So the SK, 7SK82, 85, these are dedicated motor protection relays, whereas the 7SX85 and 7SX82 we call universal relays. So it's a relay where you can put whatever function you like inside. So we have a large variety of combinations available. And also the motor protection, therefore I put them also here. The advantage could be that you have just one kind of device, the 7SX82 or 85, and you can use this device for the motor protection, but also for any other protection purpose in your field. So the idea is you have a universal device, you are more flexible, you need less devices on stock, for example. And here the small relay, the 7SX800, is also a universal relay here. Here the idea is more that we have already a lot of functions on board with only a few subdivisions or variants. So in that way we have also the possibility to put motor protection functions inside, although this is not only a motor protection relay. Good. So here the functions based on current measurement. Then if we go one step further, we have a voltage transformer, and here we can use also these devices as already explained. SK85, SX85 additionally, and here we use current and voltage measurement, so we have additionally voltage dependent protection functions. And finally, for the larger motors, we can apply a differential protection. So you see we have here a second current transformer for the differential protection. Here, however, we cannot use the 7SX800 and the 82 relays because they have just one current transformer input. Here we need to go for the modular devices SK85 or 7SX85 so that we can add one more current transformer and make the differential protection. So for the asynchronous motors, it's those relays. For the synchronous motors, I would like to mention also optionally the 7UM85, which is basically the generator protection relays. So it has much more functions, many more functions than we have here for the motor protection, but it includes also all motor protection functions. So this could be an option to use also for the synchronous motors, for example. Good, so here additionally the differential protection. So for some of our motor protection devices we have an ATEX certificate. That means they can be used for the protection of motors which are in explosive environments. For the ATEX relevant protection functions, we fulfill the SIL 1 requirements according to the IC 61508 standard. So these are dedicated devices, so we have a special ordering variant because we have a dedicated firmware, a dedicated hardware, and even a dedicated manual for these devices, for the application of these devices, which we tested at a test institute so that we get the ATEX certificate. So we cannot do this for each firmware, for each new firmware separately. So therefore it's a dedicated setup of functionality which was tested and certified. But anyhow, it is for any kind of motors in explosive environments. As already mentioned, I would like to discuss one example of settings of the protection functions for one example of a motor, rather than going more into the theory of the motor protection functions. So the idea is to approach this more from the practical side. So therefore, I took a motor data sheet and made some extracts of the relevant data we have, and that's it. So we have, on the one hand, we see here it's a motor with almost 6 MVA or 6 megawatt batteries with 6 kilowatt and a nominal current of 640 amps. So could be already something like we saw in the picture before from the size, relatively high. And we see the starting current or locked rotor current, which is nothing else than the initial starting current when the rotor is at standstill, is 5.6 times the nominal current. For the nominal voltage, which is normally rather a theoretical value, in practice normally we have a voltage drop, and this is given here for 90% nominal voltage. Then you see we have a starting current of 5 times nominal current roughly. The starting time here is 4.5 seconds, respectively 6.5 seconds with a reduced voltage, and reduced voltage, lower starting current, longer time, so therefore 6.5 seconds. And the motor manufacturer tells us we can start 3 times in a row from the cold state or 2 times from the warm state in both conditions. So at the nominal voltage, but also at 90% of the voltage. So since the starting with a reduced voltage is more stress for the rotor, more heating up, you see when we start with a higher voltage, we have even some leeway, basically. So this would be the application. I use a 7SK85. At first just the overcurrent protection, and then as an option also the differential protection setting here. So we apply a second current transformer in the start point, and we have also the voltage transformer. And for a current of 640 amps, nominal current, I mean, we selected here a current transformer of 800 amps to 1 amp. So it's roughly like the nominal current, around the nominal current. Then we have a second information, a diagram here, these curves. We see here running motor and locked rotor. So the running motor is more the thermal curve for the stator, and here this is more for the startup. So here we have more the problem on the rotor side with the temperature, with the heat. And you see we have here 2 curves with a cold and with a warm state of the motor here. And what we can read from this diagram, if we don't have these as figures, so we have to go there and read, and then we find out this distance here is 1.13. And additionally, we get the information for the time constant of the motor, especially of the stator here. And we see here we have basically 2 time constants, the short-term load variation time constant and the long-term load variation time constant, or we can also say copper and iron time constant. So for the rotor thermal function, we need the longer one, so the long-term load variation. And then we have a second value here. This is when the rotor is at standstill, then the heat without ventilation gets out much slower out of the motor, so therefore I have a longer time constant. So what we can get here is the starting time behavior supervision, what we finally have. Here I can read any kind of pairs of values, and here it's rather uncomfortable along this line because I have somewhere always a gap to the other line here for the y-axis. Only here at the 3 I have roughly a crossing of the characteristic with a line, so I take that one and say here I come out to 31 seconds, so it's a small gap if you don't see it, and this I have with 3 times nominal current, and I can recalculate this to our starting current, which I do later. Good. Let's talk first about the general settings. Here we see now our Dixie 5, so I tried to also give you a first impression how to make the settings in the Dixie 5, our universal programming tool for the protection relays. Of course, it's not like a Dixie course, therefore we need to spend a couple of days to get all the features, but the idea is that you get the first feeling and you see how this works, basically where we can make the settings as a rough idea already. Good. So under the power system, we have then so-called measuring points for the currents and for the voltages. And here we enter the data of the current and voltage transformer. So here for the current transformer, 800 to 1 amp, and the direction of the start point of the current transformer, called neutral point, in direction of reference object. So what we see here, the start point of these three current transformers go towards the motor, and this is then the orientation for any direction related function if we need that later. Then we have another tab here for the voltages. Here I enter the voltages of the voltage transformer basically. Okay, then every function group has a general setting which describes, or maybe one step before, every function group we have in the relay describes something, an object on the primary side. So we can have a function group for a motor, for example, for a circuit breaker, for a disconnector, for a line, and so on. And the idea is, in such a function group, we collect all the functions, we put all the functions inside which have to do with the protection or other functions in general that are related to this primary object. So we can also say this function group is like a container, which is like a box where we put all the protection functions inside. I think this picture is quite helpful. Okay, so each function group has some general settings that describe these objects, and this is normally the nominal current and the nominal voltage. So we set this in the function group because sometimes we refer to these settings as a percent value, and this is then the reference. So we see that here we have a function group motor or motor stator. There's a little bit of speciality. Motor, generally we need to use a function group motor stator if we use a differential protection, a dedicated differential protection function. Okay, but basically it's the same for the application. And you see we put here the rated apparent power and the voltage, and then the relay calculates us the nominal current of the motor here. Good. Let's go to the overcurrent protection. How can we set the stages? Here is, let's say, the current trace, like RMS values of a motor start. So we have a short, very short, but high peak. Then we get a rather steady state starting current, and shortly before the motor comes to the running state, to the normal operating mode, then the starting current drops down to the load current, which is needed in the special situation here. And with the overcurrent protection, we cannot distinguish where, in which phase the motor is. So if we want to have a fast tripping stage, we need to place this over this peak value, and this is what I indicated here. So with an instantaneous stage, with no time delay, we should go over this peak value, for example, to 130% of this peak value or transient start current, what we can say. This is a relatively high value. So the idea is I take a second stage, which I can put much lower, lower than this peak value. However, then I need to be careful with the tripping time so that I don't trip with this peak current. So I need to have a small time delay here that this peak current does not trip this stage here. And here we can set 120%, for example, of the starting time, and we need a certain delay here. The delay and also the level here of the setting of the other stage we can test out during the commissioning of the motor. We can make some fault records and then see how big is this peak really in the reality, and then adapt our stage. And also here this time, we can say how long is the time between or for this peak here, and adapting also our delay time here accordingly. Then we see here two more things. Here we recommend to use an RMS value. Why? Because we go on this peak value. It's a relatively high value, and we want that so if we have a short circuit which should be above this value. It should be, or let's say there's one effect that works against this, and this is the current transformer saturation. With an RMS value, we get more of the current out than with a filtered value. So to work against possible current transformer saturation, it makes sense to use the RMS value. Here, on the other hand, we want to get more close to that starting current here. With a filtered current, we eliminate some disturbing, let's say, current, which can come from a DC component. Therefore, we filter this out better. Therefore, here the idea is to use the fundamental measurement, so the first harmonic basically. Okay, if we take our values, then calculate this here, then we see we have here 9,318 amps with no time delay, and for the other stage we come then to 4,300 amps, and we apply first 100 milliseconds as a time delay. How to make the settings? So we go into our function group motor or motor stator. Then we find here the function for the overcurrent protection. If we double click there, then we get the stages. So they are all one below the other. So in the first stage, we then can use here the settings for the fast stage. So I take here the RMS value, then the 9,318 amps and the time delay of no time delay, sorry. And in the second stage there we have the time delay with this 100 milliseconds, and we have the lower value with the 4,300 amps, and we use the fundamental component for the evaluation. If we want to make an even better protection than this relatively simple overcurrent protection, then we can go for differential protection. Here we can set basically two stages. The sensitive stage, you see the threshold is relatively low, much lower than the normal nominal current of the motor. A good starting point would be 20% of the nominal current, and we don't need a time delay. And you see we have now two advantages, a very sensitive stage and a very fast stage, the combination here. And if we want to make an even faster tripping on high currents, we can apply here our fast differential tripping stage, which we recommend to put across above the starting current, and also have a time delay of 0. Why there? Because we have a lot of stabilization in the sensitive stage, for example, against current transformer saturation. We see this later, which is not there in the fast stage, and for this reason it is the fast stage. So it's a good subdivision of the jobs, we can say. So here we are sensitive and stable, here we are fast on the other hand and not so stable, therefore we have to go up with the threshold. Again, you can test this out during the motor starts, during commissioning, and if you see, okay, there is no problem if I reduce the fast stage, then you can also try to do that and leave it. Okay, these are the tripping characteristics, the sensitive or the normal one, and the fast stage here, the dashed line. And yeah, basically if you don't have any specific ideas about the setting, the rule is leave the standard settings. They are tested, and it's a compromise between sensitivity and of course stability against overfunction, against wrong trippings. This is what we want to avoid. Therefore, these settings here, maybe just one word for warning. If you come from the SIPROTEC 4 world, there the differential protection, the characteristic had other values because the calculation of the stabilizing current was done in a different way. So here the stabilizing current is the maximum of all amplitudes on all the sides. So for the motor we have just 2 sides normally. Whereas in SIPROTEC 4 it was the sum of all amplitudes or absolute values. So there is a difference, and therefore if you copy just the settings from the SIPROTEC 4 here, then you will get a tripping characteristic which is much flatter and much too sensitive. So it goes into the direction of an overfunction. Okay, so the settings for the differential protection you find here in the function differential protection. And basically here we have the standard settings. And for the fast stage, so this is for the sensitive stage, and for the fast stage, we have to adapt the threshold. So here I set it on the maximum starting current value, basically. And in each case, no time delay, because we want to be fast here. Then for the sensitive stage, we have one more add-on, especially for motors, because motors can have a longer startup phase with an elevated current level. That means this can be also risky for the current transformers, and therefore we have optionally the possibility to raise the tripping characteristics, or just the sensitive one here, during the starting phase of a motor. This we can do with this additional block here of settings, the starting detection. And we have here on the one hand a threshold where we say if the current drops below this threshold, we say okay, we go to the standstill mode. And in that moment we already increase the tripping characteristics, so that when we switch on the motor, then it's already right from the beginning less sensitive. Then we have a factor here, typically the factor 2. That means we raise the characteristic by this factor for the time we see here. And now you see, that's a little bit a philosophical question. If you want to use that value or just the starting time, the regular starting time of the motor. Here we see besides what happens with the characteristics, so we increase or we multiply with this factor here too. We multiply the threshold and we multiply also the first slope here. And the second slope is far away, so this remains as it is. So we get this green characteristic here. And now the question is, what happens if I have a heavy start situation because, for example, the voltage is quite low during the start, so we know then the torque drops down, so I have a longer start. In that case, I personally would think about not to release that tripping characteristic to the sensitive stage if the motor is still in the startup phase. Therefore, I took here a value which we see later, which is the maximum starting time coming from the starting time supervision. But again, this is, as always with a setting, there is always a portion of philosophy behind it or personal taste, what is required. Good. So we've basically two types of motor differential protection. The one is like the classical differential protection with a current transformer in the start point and also on the line side. And here are the settings as discussed before. For the motor protection, we often have a variant where we use here a window type current transformer for each phase current, where we bring the current in one direction, which goes to the motor, and we go back in the other direction, so that both currents in the normal situation cancel out each other. That means we make the differential current in the current transformer itself. Therefore, we have here just an overcurrent protection function that looks on this differential current coming out on the secondary of this window type CT. Here you can also start with a threshold of 20%, make some startups of the motor and see what really is measured by the relay or by the whole measuring chain, so the current transformer plus relay. And then you see if you have a very, very small value always, then you could think about also to reduce this threshold maybe to 10% or so. Now let's come to the overload protection. First, let's talk about the stator overload protection. So here you see how a motor is mounted. We have here the rotor and here the stator, and we have protection functions for both of them separately. So let's first have a look. Here's also a stator, a larger stator here. Let's have a look on that. So we talk about the stator, and we have here a thermal overload protection, which is our universal thermal overload protection. That means The same function we apply also for a transformer protection, for example, or for the generator or any other dedicated objects. Behind this stands a temperature model. There is even an IEC standard for that, which is a single body model. That means we have a thermal capacitance and a thermal resistance. And it's like an equivalent circuit for currents and voltages. And if you know that, you can also calculate immediately with the quantities that are related to the temperature. So instead of a current source here, we have a power source. This is the thermal capacitance. So we don't have a voltage here across this capacitor, but it's a temperature difference. And here the resistor. And here we have a voltage source, which is basically a temperature difference source. So if the ambient temperature is different, we need to use this additional source here to describe that situation. And this can be also negative value. And we have a reference temperature here, which is normally 40 degrees. Okay, and that should it be for the theory, basically. So with some math, we come to a solution. So we have some description of the temperature behavior, and this is first in per unit values, and we have we have an E function here. If I have a jump in the current, then I will get another end temperature after some time. This would be then here the θ2, and the momentary temperature follows this E curve from the original temperature θ1 to θ2, like an E function basically. The end temperature we can calculate with this formula. So it's the current, the actual flowing current, divided by the maximum allowed current to the square. So this is a relatively important relation. So the temperature which is calculated is proportional to the square of the current ratios. And if there is an elevated ambient temperature, this is added automatically. Not automatically, it's added on top of the temperature. And we trip when the maximum temperature is reached. And since we use standardized values, this is 1. Okay. So on the reaction on a temperature change can be either the temperature on a current change, can be either the change of the temperature going up or going down. Basically, it's the same description mathematically. The summary of all that, for the maximum current, which is described by a K factor, K times IN, we reach the maximum temperature, which is 1. And then we need to make the tripping, to give the tripping command. All the values we see in that function, also on the screen, are dimensionless values. In reality, we see percent values, but it's like a fraction. And to define the behavior, we need just a few inputs to tune the model to the real existing motor. This is the nominal current of the motor, the permissible overload factor, this K times IN, and the time constant, the thermal time constant for the whole thing. The time constant describes basically how fast we move from one temperature point to the other one. With a high time constant, we are very slow. With a very small time constant, we are very fast to go up there. And the time constant, if you don't know it, you can directly draw on such a curve. You take the inclination here on the starting point, and then when you reach the end temperature with a straight, then you go down, and then the time difference is equivalent to the time constant. Okay, we have a permanent thermal image here with this function. And the advantage here is that knowing the starting point, if we have an excess current and therefore we will overshoot the maximum temperature. So knowing the starting point, calculating this all the time, tracing the currents, we can react in a proper way. So if we have already a high temperature level, then the time to trip from here is faster than if we start from somewhere below. Or if the motor is switched off, then we are maybe around 0. So we have a longer time until we need to give the tripping command. That means there is time that the situation settles down and we do not come even close to the maximum temperature here. I put here the formula for the calculation of these tripping times. So if you're interested, this is the preload current that must flow for a long time so that the temperature is corresponding to this current, so steady state situation. Then we have the new current here, I, with the K factor and a possible ambient temperature in here. And with this we can calculate the tripping time. Okay, so I don't explain how to come to these relative values here. For example, if you are more interested, we have another webinar, or it's also described in the manual, not to blow up too much the whole thing here. Okay, so settings for the state overload protection. We have the K factor here, which we find by measuring this value here, so the distance here from the y-axis. This is our K factor, and here if you measure that, it's 1.13, for example, which is a rather normal value. And we get also the time constants here. So here we need more the long-term time constant, and another one is the time constant when the motor is at standstill. Then we have a less airflow normally, in that case at least. So it takes much more time that the heat goes out, therefore we have also an extended time constant. If we have a look on the settings, first we are to find the settings in our function group motor or motor stator. We double click on the overload protection function, and then we get here the settings for this function. And yeah, what we add here is the K factor on the one hand, so this is one of the fundamental settings here. Then the time constant, the normal time constant when the motor is running, so this were the 20 minutes before. And also the time constant when the motor is at standstill. So here we put 300 minutes, we have to set it in seconds here in this case. Then we have a current which describes us when is the motor running and when is the motor at standstill. And here I took primary value 64 amps. This is 10% of the nominal current. And I know normally the no load current, the smallest current I measure when the motor is running, is around 20%. So I'm below this value, and I know, okay, if I go below this current value, the motor is at standstill or soon comes to a standstill when it's switched off. At least it's switched off, it's not working anymore. And then I need to apply the longer time constant. Then I have two warning thresholds. The first is a current warning threshold. So here, practical approach is to take K times IN. So if I go over that current for a longer time, then I will overshoot the maximum temperature. If I'm below, not. So this could be a good warning threshold. And for the temperature itself, we need to think about the maximum temperature is 1. What is the temperature under nominal conditions or normal load conditions? Let's assume it's the nominal current. Then you find out that this temperature is 1 over K squared. So in our case, 1 over 1.13, which is 78%. That means, yeah, I need a value somewhere in between, and I just left it at 90%, which is all our default value here. What else is here? Yeah, the dropout threshold. So here it means if I go beyond the maximum temperature, beyond 100%, then I will give the tripping command, and this will be kept until the calculated temperature, when the current has disappeared, until the calculated temperature goes below this threshold, this drop-off threshold. That means the contact remains closed and you have some kind of blocking against an unwanted closing of the breaker, for example, so you can use it in that way. Then we have the option to store the thermal replica in case the auxiliary power fails in the relay, I recommend to switch this on all the times, because in such a case, think about you have 85%, for example, and you have a small outage of the auxiliary power for whatever reason, then without the storing, you would start with 0. So you have a big gap between reality and the starting point in the thermal image. That means it cannot be correct. Good. Then we have a couple of settings, a few settings, only if the ambient temperature is different to the reference temperature, which is always 40 degrees Celsius. There we can enter the other temperature, and an approach could be to use, if we don't use a sensor for the ambient temperature, we use the maximum temperature. So for example, 50 degrees ambient temperature. The K factor here remains the same, but the relay recalculates or takes into consideration the higher ambient temperature, so the maximum current will be reduced. So with a smaller current, you will see that you come to the maximum temperature to the 100%. So in that way, it's somehow integrated in the calculation. Okay, to make that correctly, we need somehow a relation to the absolute temperatures, and this is this setting here. This is the difference in Kelvin between the temperature under nominal current and the temperature without current. So difference, or the temperature increase when you have a nominal current flowing. And if you know that value, then we enter it, and then the relay can handle the situation with a different ambient temperature. The reason is we use this per unit values or standardized values or scaled values, we can say. And here then some absolute temperature information is missing. So if we want to refer to another temperature, reference temperature, like the ambient temperature, we need to add this information here.
Okay, thank you, Klaus. So this was the first part of what we wanted to talk to you about. We've already gotten some questions that we'd like to share with you. Thank you for all the questions that have been coming in. The first one, will this webinar be recorded? And the answer to that is yes, very clearly. This live stream session is being recorded so that we can offer it for viewing for additional participants later on demand. Just use the same registration link you used for today's session, and you can view it again or share it with your colleagues and customers. So let's look at the first question, Klaus. The question is, when should I select 7SK82 and 7SK85 for motor protection applications, and when can the 7SX800 work, and why?
Yeah, the 7SX800 is the smallest motor protection device as regards the binary inputs and outputs. If you compare all the functions for motor protection, they are quite similar, all the devices, with one or two exceptions. One exception is that the SX800 and the 7SK82, they both cannot be used for a differential protection because there's no way to add a second current transformer. So if you want a differential protection, you need to go for the 7SK85 or for the 7SX85, which is the universal relay, which can have exactly the same functions as the 7SK85. And the other bundle of functionality, which is not in the 7SX800 and the 7SK82, are the protection functions for synchronous motors. So this is basically the out-of-step protection function, the under-excitation protection function, and in the 7SK85 we build in also the rotor ground fault protection. I think that's the difference between those. So if you have small applications for small motors where you have just current inputs, then use please, or you can go for the 7SX800, depending on how many IOs you need. Then the next step is the 7SK82 or 7SX82, where you have more IOs. And then the next step is the 85 relays, SX, SK85, or even the 7UM85, where you have a large variety and flexibility and the possibility to add many binary inputs and outputs.
Okay, Klaus, another question came in. It's probably having to do with existing systems that are being retrofitted with motor protection. What protocols do these devices speak?
Yeah, so the devices speak first IC 61850, which is, let's say, not the standard, the big standard maybe for the industry, but the big standard for all the utilities. Then the Modbus TCP. Here we recently added the client functionality. That means you can also connect sensors from the field directly to the motor protection or to the SIPROTEC 5 protection relays in general. Then we have Profinet IO, DNP3, and IC 104 for the Ethernet protocols. And if you talk about the serial protocols, we also have them. That's the IC 103 protocol, Modbus RTU, and also a DNP3 protocol.
I hope there's no test at the end of this. I won't get all that.
Sorry, again, no, it's not tested. I also wrote it down here, to be honest, because I did not want to miss one of these protocols.
Okay. LW asked us, I have a motor differential application with 2 feeders, and there are 3 measuring points needed. Klaus, can you take over that?
Yeah. I guess you have somehow 2 infeeds to the motor, like we can have for a transformer, for example. Then I see 3 measuring points, and we can handle that very simple. That means you saw for the differential, we have 2 sides for getting the currents, and in one side you can add 2 currents, and from the other side, in the start point, you have the other current. So in total 2 sides, and it's a very common and simple topology we can handle. Because the motor diff protection is, I don't remember if I mentioned it in the video, but it is basically like the transformer differential protection simplified, because not everything is needed there.
Okay, PS sent us a question. For the stages first and second parameters, how do we use that? We're not really sure. If you are PS and you put that question in, could you give us a little bit more of an idea of what that is you're asking us, so we can come back and give you a good answer?
Yeah, so the relation to, so which settings you really mean? I saw it was during the diff protection, but I could not get really the connection, which settings or parameters you are referring to. So maybe you can give us another hint there, please.
And there was one other question that came up just simply about SIPROTEC 5 as a family. I'd like to mention before we go back to the next part of our webinar today, if you're not fully familiar with our SIPROTEC 5 portfolio, please feel free to take a look at the beginning of the first session of the motor protection, because there Klaus showed us the portfolio and the applications and why some of the design parameters are there for SIPROTEC 5. So with the same registration link, you can select to watch the first webinar in the series, and there in the first 5 or so minutes, you get a good introduction about the SIPROTEC 5 family.
Yeah, and especially the benefits we see for SIPROTEC 5 as a system, as a total. So it's not only for the motor protection, it's embedded in the whole family, and there we have some nice system features, I would say.
Okay, Klaus, shall we move on?
Yeah, okay.
Okay.
Let's go on.
Thank you. See you soon.
Let's have a look on the motor monitor function. Before we go to the temperature calculation for the rotor. The motor monitor I explained in detail in the first webinar, where we talked about the overview of the protection functions. Therefore, I just put it here again. And maybe some words. We have this state detection, or the state model we use, because some protection functions are dependent on the state, or we can also say they are active only for a certain state. And there we have 3 of them. The first is the restart inhibit function, which is active only when the motor is at standstill. The reason is this is a function that prevents against the starting of the motor too early. So if we have too many starts in a row with too less time, then this function forces us to wait until we restart the motor. And therefore it's active when the motor is at standstill, because only then we can switch on the motor, and then it's relevant. So if the motor is starting up, we have the starting time supervision to monitor a too long start. And when the motor is running, we have the load jam protection. And only there, because if this was active all the time, we would probably trip with this function with the starting current. This is what we need to avoid. So therefore this goes active only when the motor leaves the starting state and remains or comes to the running state. Here are the conditions, how we come from one state to the other one. I shortly explained them in the other webinar, so if you're interested, go and have a look there or have a look in the manual. So let's have a look on the settings for this motor monitor. We get the settings if we click here on the function motor monitor, and you see we have just a couple of settings here. The first one is the starting current of the motor. So you should put this somewhere between the load current and the minimum starting current with a reduced voltage. That means doing this, you know, if the current exceeds that threshold, it cannot come from the load, and it cannot come or it will come only from the starting current, and the minimum starting current is above that threshold. So it's a safe place to put it somewhere in between. Our starting current is what was it, 5 amps, something like that. If we go back, so we have 2.5, it's much higher than the nominal current, so this could be a good value here. Then the frequency setting is for a special situation when we have several motors in parallel that are switched off. Normally, when a motor is switched off, you would expect there is no current at all immediately. Now, if you have more motors, then one motor can feed the other motor, so it's not a fast criterion to look only on the current. But looking on the frequency, this criterion is much faster because the frequency drops down immediately from the grid frequency to the frequency of the rotor, and then it collapses or goes down fast, because the rotor must maintain the own driven machine and also feed the power for the other motors. So this goes rapidly down, and this is important so that our load jam protection does not trip in case we have a restart of the motor with a higher starting current. So we need to understand quickly that we leave the real normal operating or running state of the motor. Therefore we have this frequency. And here it is rather low, the setting, the standard setting. So if you know your grid frequency, normally never drops below 49.5 Hertz or 59.5 Hertz, depending where you are. Then you can set that value, so you have even a faster reaction here. Then we have a current threshold that indicates that a motor is restarted again. So normally the restart current is relatively high immediately, even if you have a short voltage interruption. Here we put another setting additionally to the circuit breaker open threshold. So the circuit breaker open threshold is to detect that the circuit breaker is open. We use this to go to the standstill, and here with another value to say, okay, the motor is starting. I set this to 15% here because a motor that is running without load has already 20% around that value. So I'm below. So, or the other way around, if I have a value that is higher than this 15%, I can be sure the motor is running. And finally, we have a time delay from the slowdown state to the standstill state. Here the idea is, if I have a switch over on the bus bar, fast bus bar transfer, or a normal bus bar transfer, I want to stay in this slowdown state as an intermediate state so that I can correctly detect a restart. If I stay not long enough in this slowdown state and I go to the standstill state, then this restart inhibit function will become active, and this will then trip the circuit breaker. So this needs to be avoided. Therefore, this time should be longer than the switch over procedure from the bus bars. Okay, let's come to the rotor. Here we have two functions: protection against a too long start or locked rotor, and the restart inhibit function against too many starts in a row. Therefore, first we have to talk about a thermal model. Again, we use the same model also for the rotor, but with different parameters. So we have two models running in parallel with different temperatures normally, one for the stator, one for the rotor. And the given data to feed this model from the motor manufacturer is the number of starts with a cold, with a warm motor, and the corresponding starting time and starting current for which these two values are valid. So normally it's even the startup time and current with a reduced voltage, which is somehow more stress even for the rotor than with a nominal voltage. So you can enter those two, and then you have the maximum, leeway for starting up. So from these given values with some maths, we calculate also a K factor for the rotor and a tau, a time constant for the rotor. So similar to what we do with the stator. And to give you an example, a very standard example here, what we have, we see the time constant is relatively short, not even 3 minutes, and the K factor is relatively high. The consequence is that the temperature under nominal conditions is relatively low. So we talk here about the rotor again. And the temperature overshoot, if I have the locked rotor situation and I let this current run forever, you see it's more than 8 times the maximum allowed temperature. So this is what we see here. I put here some formulas if you're interested how to calculate these values here. And yeah, we now talk about the temperature calculation only in this tiny part here, so from 0 to 1. And also here we have a thermal model which we apply, so same calculations similar to the stator thermal model. And we trace the temperature also all the time. That has the advantage that, depending on the situation, we know how much temperature range is left over, or reserve, we can also say. So we can understand if we can restart once more or if we cannot restart once more. So from this thermal model, we derive the restart inhibit function, which has only a very few settings, and also another function, the rotor overload protection function, which is rather monitoring the temperature. And if this reaches here 100%, it gives a tripping command, if you like that. Okay, let's have a look on the settings for the thermal replica rotor. We find the settings here in the menu motor or motor state in this function group, and then there is one function thermal replica rotor. And if we double click here, then we get here our settings. First, we have to enter the number of warm and cold starts, which we get from the data sheet. In most of the cases, this is the combination 3-2. Then also from the data sheet, the starting time and the starting current for which these 3 starts are allowed. So normally this is the starting which is either under the nominal conditions or the load conditions if it's a specially designed motor here. Then we have a setting again if you want to store the thermal replica or not. We recommend always to switch it on so that the temperature is stored in case there's an auxiliary power failure. Therefore, we are on the safe side. And then we have 2 more factors. The one is if the motor comes to standstill, then the cooling is going much more slower down because the rotor is at standstill, there's no ventilation. So for this we have here the second factor, T constant standstill, and we have another one built in. This is for calculating the temperature down when the temperature goes down, when the actual current is lower than before. So we have here a possibility again to be more on the safe side, to go slower down than going up with a time constant. So we can also extend here the time constant. Okay, then we have a setting, the equilibrium time. This is for the restart inhibit function. This comes next. I explain a little bit better and with a diagram what is the sense of that. And finally, for the starting time supervision, we have here the threshold, the temperature threshold, to switch between a cold and a warm motor. So also for this function we have two curves, which we normally also get on the data sheet of the motor manufacturer as we saw it at the beginning. And to switch over between the one and other characteristic, we have this setting here. We learned that our nominal temperature of the rotor is around 35%. I mentioned that before. This comes out of the calculations which we had on this sheet there on this slide. And now there is a compromise between 0 and 35, so somewhere in between that's a switch over, and we should not do this exactly at 35%, because then if we are at 33% or 34%, we would still have the cold motor situation and the longer starting time. So it's a good compromise to go somewhere in between, so to 20 or 25%. If you go further down, we are more on the safe side. If we go further up, we are more a little bit on the challenging side, let's say. Okay, so now from these settings we have the restart inhibit function deriving from this thermal model. Here we have only a few settings, as you can see on the slides. The first one is a little bit special. It's called automatic restart inhibit. That means if I set this to yes, then I do not produce only, or the function does not produce only this restart inhibit signal to block a closing command externally. Automatic means if we use the internal control function of the SIPROTEC 5, it prevents the closing command and it keeps the tripping command. So it really, so you open the motor, and at that moment it keeps the tripping command closed, or it trips the motor basically. If you don't want that behavior, then you set this to no. That means you have just a signal restart inhibit, and you can use this signal to block the reclosing externally. Okay, what else? We can switch it on, mode, and then we have the minimum restart inhibit time. So this is just the time going in parallel to the calculated restart inhibit condition. So if we switch off the motor, then this is a minimum time when we are above the maximum temperature, this restart inhibit temperature, that we do not allow the reclosing. So the second function that comes from this thermal replica rotor is the so-called rotor overload protection. This is simply an overload protection that gives a tripping command if we reach the 100% value with this calculated temperature for the rotor. If you use that, then you will trip as soon as we reach the 100%, which could be not the desired behavior if you are in the startup, which maybe overshoots a little bit, and it goes maybe to a maximum of 105%, and at 100% you give the tripping command. So if you want to avoid that, then set this to alarm only, or in this case the name is with SIPROTEC 5 operate and fault record blocked, yes. So it just produces an alarm and no tripping command, and then you get just the indication you're above the 100% value for the temperature. Okay, here I have a curve basically for the thermal stage of the restart inhibit function. We have here the starting phase, so motor is starting, then the motor is running for some time, and then the motor is switched off, and then I have two more cycles like that. And you see two things. First thing is the warning stage or the warning signal comes as soon as we overshoot the maximum restart temperature, restart inhibit temperature, this limit. This limit means that if we are there, we can make one more regular start as described in the parameters before. So the time and current we entered here as parameters. And as long as we are above that value, we have this warning stage. So this characterizes that we are above this value. Then we have the restart inhibit signal itself that comes up only when the motor is at standstill. So the relay detects motor standstill state, and then we have this signal coming. And now this equilibrium time we were talking about, we saw the setting before, now comes into the game. Because when we switch off the motor, the idea behind this, you see this also here indicated if we follow the black line, then we have here a straight, a parallel to the x-axis, so we keep the temperature constant for this equilibrium time. What is the idea behind? You see here we have a red and a blue line and this black line. So the red line means we have some zones where we have basically a higher temperature as in another place of the rotor. You see here upper bar, lower bar. We cannot calculate these temperatures with this model. We cannot calculate where is the temperature, how much, and how's the distribution. What we do is to assume a kind of medium temperature, which is allowed because based on that medium temperature, we follow just what is required, what is the requirement or the scenario for the startup allowed by the motor manufacturer. So we have these 3 starts from cold and the 2 starts from warm. And this gives us, let's say, this black curve, which we calculate. So in this equilibrium time now is the idea that we say, okay, we give the whole system a certain time to recover, to balance out the temperatures there where it's higher on the upper bar of the rotor bars, or where it's lower on the lower bar, so that these temperatures can balance out a little bit before we go and count down or count up again the temperature. So this is 1 minute if the motor is at standstill, and if the motor starts, then this time of course is interrupted, or this signal is interrupted, but this is then an emergency start because you cannot start if you have the signal on normally, if you use it as it is designed or planned. So if you have a look here on the when we exceed the threshold, then when we switch off the motor here, we see again I have the signal, and the signal now is longer. It is minimum the equilibrium time if there is a setting different to 0. Then it's longer than the minimum time. So this was one of the settings we had before, the minimum restart inhibit time. And here in our example, this here elapses, and then we are still above the value. So the restart inhibit signal is still kept until we really undershoot this temperature again, this restart temperature again. So this is basically what is behind. So you can use this restart inhibit signal, which comes automatically when the motor is at standstill. And we have the warning stage, which you have as an additional information when we overshoot the restart limit. Okay, let's go to the second function for the rotor overload protection or temperature monitoring. It's the starting time supervision, ANSI code 48. Here the trick is the following, or the principle is the following. We have again here the starting curve, and it's also an example here again similar to the one I showed before here, and I want to focus on one small point here. We only look again basically at the range between 0 and 1. 1 is the maximum temperature here, and if we zoom in here, then we see this curve here, which is again an E function, of course, looks more or less like a straight. This is because we have just a tiny part at the beginning, so the time we need until we come here to the maximum temperature is only a small share compared with the tau. So that It's just at the beginning, and therefore I have more or less like a straight here, the behavior. Okay, and this means for the supervision of this startup of the motor, the starting time supervision, we use a simplified model. Let's have a look on the settings. So I pick again here the setting, pair of settings of 3 times nominal current, and then if I go up, it's 31 seconds here. Practical approach, if I have just such a diagram which is rather unprecise to read, if I go to a value like here, for example, then it's just a little bit guessing which value exactly is this here on the y-axis here. Therefore, the idea is I search me a point where the curve here really cuts one of these lines so that I get a more precise value, and therefore I've here this couple 3 and 31 seconds. I can recalculate this now. Let's see if this comes here on the slide. I can recalculate this now to my starting, my values which I get in the in the data from the motor manufacturer, so that it fits here together. At the end, it's not really interesting, because if I take that value pair here and recalculate it, I will follow this line directly. On the one hand here in the function, on the other hand, also if you compare the times and currents in the data sheet of the motor, this again follows exactly such a line here. This is what we see, what we see here, but this follows also, we follow also this line in our protection function. So this goes really in the same way. Therefore, I can make that recalculation. I would recommend it, because then you make the correct settings according to the starting current, which is really as a given data, and not, you don't take this one here. Maybe someone could be confused if you enter these values instead of the real starting current. At the end, it comes out to the same value. Okay, how to do that? In reality, in the data sheet, I have the starting current of 5 times nominal current, and we can now calculate the starting time, the corresponding starting time here, which corresponds to the 31 seconds, by taking the starting time of the, so I take here the starting time of the 3 times nominal current, the 31 seconds, and then I multiply this with the ratio of the current, so the 3 amp current divided by the 5.01 to the square, as you see here in the equation. And then I get a time, which is of course shorter because the denominator is bigger. That means I go down this line here, and then I'm at this point here, and if I make that calculation, I come to 11 seconds. So this here would be 11 seconds. And the same I can do for the warm characteristic, warm motor starting characteristic. So I take the 20.5 seconds, and then I come to 7.4 seconds. Good. Yeah, the function itself is based on a little bit simplified model. So we see here the simplification is this switch is open. So that means we don't consider any energy that flows away during the starting process, because there's so much energy created, heat created in the rotor during the starting process, and it's a short time only. So we can neglect that. So we don't have the E-curve really. I have more like a straight. As a consequence here, and this needs to be understood, first I have a tripping time or tripping characteristic that is simpler, so there is no logarithmic function anymore inside. It's just here an inverse time, kind of inverse time square function here. It's not really exactly like an overcurrent inverse time function, because there's still this thermal model behind. This is more precise. So what we do, basically, we integrate up all the currents to calculate a temperature permanently. Whereas the stripping time is always only valid if I have a constant current flowing here. Good. Also with this model, I need a starting condition, because otherwise even a very, very small current will load up here this capacitor, or better in the thermal model speaking, a very small power will heat up this capacitor or this thermal capacitance. That means I would get a too high temperature after some time. And yeah, because this part here is missing, so therefore I need a starting condition, and the starting condition is the motor state is starting, basically. Good. That's the tripping characteristic here on the right hand side. So we see I have two characteristics, one for the cold and one shorter for the warm motor. And yeah, I can add, if I like, an additional locked rotor tripping characteristic. And you see this is again just a simple definite time tripping characteristic. And this can be activated by a binary input. And this binary input indicates that the rotor is locked. So I need somewhere this information from, so a speed meter that gives me a contact, and if the rotor is locked, then I activate this characteristic. What is the sense? Yeah, if I don't have this and the rotor is locked, then this function will trip only after the corresponding time. So then we walk up here the time, and then when we reach the 100% temperature for the 100% temperature for the rotor, then we will give the trimming time. But we can save this time for two reasons. On the one hand, it's a big stress for the rotor, so we heat up the rotor to the maximum temperature. That means the insulation is also stressed, we can say. So I don't need that. On the other hand, if I save that time, then I can trip in a fast time. Then I can see and fix the problem, and then I don't need to wait until the rotor has cooled down again, and this can take hours, for example. So if I trip when the rotor is still at a relatively acceptable temperature level, this is then better in the way of handling the whole thing. Okay, let's have a look on the parameters, what we need to set here. First, we have the operate delay. If the locked rotor is detected, and again this is indicated via binary input here, and this is called this maximum locked rotor time here. And you see this is a relatively short time, 2 seconds. This characterizes the time we see here, this time here. This time here. Now I have to look a little bit closer here. Yeah, this is the time going up here. Therefore it's not the time especially which we get when we go up the curve here for a certain current, which could be misunderstood because it's called maximum locked rotor time. This could be the maximum time the motor can withstand with a locked rotor. Here the meaning is the maximum time I would allow the motor to stay with a locked rotor before I trip. So the idea is I give maybe a couple of seconds to the motor in that locked rotor state still. First, because I need maybe some time to detect that it's a locked rotor. And then second, there might be maybe the chance, depending on what is behind, that maybe there is a locked rotor situation for a short time, and then the motor starts nevertheless, so then I would not need to trip the motor. So therefore maximum locked rotor time, in the way this is what I allow the motor to stay in this locked rotor phase in that case. Okay, then from the data sheet here, I have the maximum starting time for the cold motor here. What do I allow here? Basically, I can use the maximum locked rotor time. I did it here, and I took it a little bit shorter than this maximum locked rotor time for the cold motor. And now in this case, the maximum locked rotor time here, the meaning is it's really what the motor can withstand before there's a damage of the rotor. So I took a little bit a smaller value because my starting time is far away from this 11 seconds, so I could say I go a little bit further down. From the data sheet, my maximum time from the warm state is 7.4 seconds. And now if I compare this with the standard starting time, which is 4.5 seconds, if I go down here, I have just a very small leeway to allow a little bit a longer start. So here I decided to say, no, I take the full time, the 7.4 seconds. So I really try to go really to the limits of the temperature here. But again, these settings depend really on the situation, how long the motor starts, how long is the locked rotor time. So basically, if the locked rotor time, the maximum locked rotor time, what you have here in these characteristics, is if this is much longer than your starting time, you can be a little bit more generous. If it's very close, then you have to think, what do you want to allow for the start? I mean, if you start and you are at 90% of the speed, for example, and then your setting here is too small and you trip, then you have not won anything. So maybe it's better than to go to the limits in these extreme cases. Okay, so and these are those two values here again. So it is here basically the two currents we see here. So for the cold and for the warm motor.
Okay, Klaus, we've gotten quite a lot of questions again, and for you in the audience, we have picked a number of them to share with you to immediately answer. The first one, Klaus, you did not mention anything about CT requirements. What are they?
Yeah, this was due to the fact that I didn't want to extend it again more the video, the presentation. So you find them in the manual at the end. Basically, it is that the current transformer should not saturate during the starting of the motor. I've also a little bit an older webinar, which I made roughly 2 years ago. There I give some examples for the calculation of current transformer. So if you're interested in that, maybe you can go back to the other webinar, the older one that's explained.
Okay, and for this and other questions like it, by the way, when you get the download of the presentation that Klaus shared with us today, you'll see his contact email at the very end if you have specific questions later.
Exactly. Download. We have also the motor application guide, which you get as a download link later. And also there is some calculation example for the current transformer dimensioning, if you like.
Okay. Klaus, the next question we have, which temperature sensors can be connected to the 7SK82? That's the non-modular version of the SIPROTEC 5.
Exactly. There you have the option to add a temperature card when you order the relay. So you cannot attach anything later for these non-modular devices. So you need to order it directly from the beginning. And then you can connect up to 12 temperature sensors, and the type is PT100 and then an nickel 100 and 120. For the SK85, maybe I can already tell that. Also an expansion module is in preparation so that you can put this beside the basic module. And there we have also done, what I know, 12 inputs for temperature sensors. So also for the modular devices, this is planned to come.
Okay, thank you. And MRC asked us the following question. How about the synchronous condenser? Can we use the same protection device here?
Basically, yes. Because synchronous condenser, it's a synchronous machine generator motor. So we implemented the functions for the motor in the motor protection in 7SK85. If you need more additional function, again, this is always kind of philosophy, what is required by the end customer, how much money people want to spend for the equipment. If there are functions that go beyond what we have in the SK85, then go for the 7UM85. There I'm sure you have all the functions which you require, 99%. You can never hit 100%, but this is a very complete device, definitely.
Okay, but the mention about a synchronous condenser, this is moving toward a synchronous motor and also therefore in the direction of the 7UM functionalities. Okay.
So it's overlapping. If motor or generator, it's the same machine. You can drive the motor, synchronous machine as a motor or as a generator.
Okay. We get two questions that are connected together from SJ. The first clause, 66 protection. We require minimum time inhibit. And is this time for the motor cooling constant? If not, how do you calculate this?
It is not exactly the time constant. Time constant is this thing in the E function. You remember, I think I showed some E function diagrams or curves. There you can get the time constant. It is not the time as such. The time, what was it, this inhibit time? It's basically, yeah, up to you if you use that or not. If you rely on just the temperature model and the calculated time until you can reclose, or if you say, okay, I want absolutely minimum time before I can reclose. This is then additionally when you switch off the motor and you're above the threshold for the restart or reclose, then you can run this timer. One approach could be to say, okay, if I'm at 100%. So I take here the time until I go down under this restart threshold and take this time as a minimum time, for example. There you need a little bit calculation because you have to calculate with the E functions, basically. So you have to see, okay, how is the temperature going down? For the cooling, we have an extended time constant. So it's a factor which is multiplied on the time constant. That means you need to know the time constant. There we have, I gave you some formulae in one of the slides, how you get the time constant from the parameters you put into this thermal model. And then with the multiplicator, you have then a time constant for the cooling down. And then you can calculate from a certain temperature, if you go down to the restart threshold, how much time this takes. I'm thinking if maybe I put a set of formula together so that you can calculate that time if I don't find it in the slides. I'm not 100% sure if this time is mentioned somewhere in the slides. I think I put it somewhere in, but okay.
Okay, and as Klaus mentioned, maybe some additional information will come. We will answer these questions in writing also afterward for all participants, and so therefore you'll get another chance to see the questions and the answers next to each other.
Exactly.
Okay, and SJ also had a second part of the same question, Klaus. I'd like to know about the ANSI 66 protection to be set based on a counter method or thermal method. And if in the counter method, what confirmations do we need from the motor vendors?
The counter means, as you saw in the slides, that you get some information like you can make so many starts in a certain time. For example, 2 starts in 1 hour, and then if you want to start again, you have to wait until 1 hour from the from the first start has elapsed, and then you can continue with the next start. You can use both principles in parallel. The one who blocks wins, basically. It's that easy. So if the timer stage or the counter stage says, no, you cannot close, and let's say the temperature calculation would allow that, then it's still inhibited and you can reclose only when your counter stage permits again to close.
Okay, we have one more question we'd like to cover right now from AG. And the question says, can you give us an example of how we can test the thermal replicate rotor function and also the ANSI 49R function?
Okay, so they are both related, as you know. The 49R function is basically just giving a warning or the pickup and the tripping if the thermal model reaches the 100%. How to test this? Again, you have to know how the E function goes, and I think the formulas are in the slides somewhere where you then can calculate the temperature, and then you can just measure the time. You put in a certain current, maybe you reset the temperature of the rotor first, then you start with 0, put in a certain current, and then see if the relay trips after the expected time. That comes with the E function, basically.
Okay, so for now, Klaus, I think we're finished with questions. We'll come back again with some more. We've already picked up some of the questions you've asked that will fit better with the third part of the subject area. Some people are asking in advance for issues that we're still going to cover. So, Klaus, let's finish up now and then bring more questions.
Okay, enjoy the third part.
See you soon.
thermal protection for the rotor, and this is all about the negative sequence current protection. We distinguish basically two issues. The one is the loss of a phase. That means maybe one fuse has tripped. Then the motor sees these voltages here, so completely unsymmetrical. And the result is a negative sequence current system. Since this is open, the current flows in and out. And if you put together the three systems, so the zero sequence system is zero, so it's basically those two systems, then you get the two currents which are in opposite direction, as we see here, in out. And this is a big stress for the rotor because the negative sequence impedance of the rotor is much smaller than the positive sequence impedance. That means the resulting current is also higher, and the resulting heating up as a consequence. So here we need to react fast, and therefore we can use a simple overcurrent stage based on the negative sequence current. And we find this again in the settings here, motor or motor stator function group. And then we have here a setting for the classical normal negative sequence definite time characteristic. And here we can set two things. First, I have to say, when do I want really to work with this negative sequence current? And here I decided, okay, I want to have at least 10% nominal current. Below, it doesn't make sense because there is not a situation that the motor is running and whatever. It could be a strange situation, so not a normal one. So this function is only active if I have some share of really nominal current, 10%. So this is then the 64 amps. And then the stage as such. I have two thresholds here, and it's also kind of experience or practical values. So the first one I set to 40%. If I have such a situation, the negative sequence current goes much higher under nominal conditions, let's say, of the motor, because the voltage drops down in total and then the current increases. So I get in reality easily higher values than this 40%. And here I have a tripping time of 3 seconds, so I don't wait really a long time. I give a little bit time to see if this is really an outage of the phase voltage here, and then I give a trimming command. So we have a second effect for negative sequence current, and this is a voltage unbalance. So here we do not have one phase voltage completely missing, but we have just a small unbalance. Maybe one phase is a little bit smaller, the other a little bit higher or bigger. And then we get a relatively tiny negative sequence system for the voltage. But now the effect comes again into the game. The negative sequence impedance is much smaller than the positive sequence impedance. So a tiny part of negative sequence voltage will create a relatively big part of negative sequence current. This is what we see here. So as a rough estimation, we can say 1% of U2 gives me something like 5 to 6% of I2. So I have also to do something here. And here we get relatively small if you compare it to the outage of one phase voltage, where we get really negative sequence current like 50–60%. Here we get smaller values, and here we work again with a thermal model behind, because we don't want to trip too fast and not too late. So we try to estimate also the effect we get from this negative sequence current on the rotor temperature. Therefore, it's called unbalanced load protection, because we have this thermal model behind. Good, let's have a look on this thermal model. You recognize maybe it looks pretty much like the one for the starting time supervision. So we have here also a switch which is open. That means we do not permanently calculate this temperature. We just go if the negative sequence current exceeds a certain value, then we work with this thermal model here. So we need also a starting value again, otherwise tiny power that flows in here coming from this negative sequence current will load up here this thermal capacitor, and the temperature will go to theoretically infinite because the switch here is open, so nothing goes away here. Therefore, we need the starting value, and the starting value is, after some maths, okay, I first have here the tripping characteristic. So it's again a relatively simple tripping characteristic. So it's an inverse time square with a negative sequence current, basically. Good. The starting condition is written here. This is the maximum permissible negative sequence current. So often you get this value from the motor manufacturer, sometimes not. Then we need to estimate, and then something between 5 and 10% is a good value normally for this negative sequence current. So the minimum, the maximum one, which I can have permanently. Okay, here the tripping characteristic. So this would be the starting value, the maximum permissible current, negative sequence current. With this tripping characteristic, we limit this to 10 times this value, and then we just keep the time, not in order to come in conflict with overcurrent protection to get fast tripping times here, really fast tripping times. Therefore, we have then, let's say, the coordination with a definite time stage again. Okay, the settings here. We have basically here we take 8% as a standard value for this starting value, and then we have so the so-called K value here. This has nothing to do with the K factor of the overload protection of the stator. Besides, it's just by incidence that there is also a K in the formula in the manual, so I kept this here. What is that K factor here? Basically, if you have a diagram of the negative sequence current amount versus the maximum time, so a time curve similar to maybe such a thing here, then you can pick the value where you have the negative sequence current, which is the nominal current. Why? Because if we insert here the nominal current, then here this quotient is 1. So you get immediately the K factor as from the tripping time. So you read the tripping time and then you have the K factor here. If you don't have such a diagram, then you have to estimate that K factor, and the conservative value is something like 3 to 5 seconds. So this is relatively fast tripping. If you have characteristics, you see that you have partially values like 10, 15 seconds or even more here. So with this 5 seconds, you are quite good on the safe side. And then we have here built in our model also a formula or a method to have a reduced drop-off. So we count down the temperature, and this cooling time, which we can calculate according to this formula, gives us a good approach or approximation to that. Good. Then the load jam protection. Now we leave the thermal model and the protection of the rotor. Now let's have a look on this special function, which I already mentioned. This is to protect the driven machine. So if there is a load jam, for example, a chunk of stone or coal or so, which blocks this machine, or maybe temporarily only or permanently, then we have two possibilities. Either we have such a function, or if not, then the rotor is blocked in the worst case, so then the thermal functions for the rotor come into the game, or also for the stator, depending who is faster. But anyhow, these are slow functions. That means the time this situation remains depends on the maximum temperature which is allowed in the rotor or in the stator, and this can be a long time. And that's not really a good solution, because in such a case, we maybe want to trip fast to safeguard the driven machine. Okay, therefore we have a load jam protection that detects rotor locking or a load jump, means a much heavier load situation somehow, which I don't want to bear, to carry on with. And the criterion here is a simple higher current, a current jump. And the second criterion is this is only active during the running state of the motor, because otherwise this function would also trip on the starting current of the motor. So we need absolutely to separate those two states. Therefore, besides, we have also our slowdown stage to quickly go away from the running state. Again, if we think about the motor state model. Yeah. And with this, we are faster than all thermal stages normally. There is a second application for that, and the second application is that it is at the same time a more sensitive overcurrent protection during the running state of the motor, because if you remember, the overcurrent protection we need to set above the starting current, and now the starting current has gone, the motor is running, so I can set a threshold which is somehow above just the maximum expected load current, which is much smaller than the starting current normally. So I have here, during the running state of the motor, a relatively good and sensitive protection. Again here, if we have a switchover, fast switchover, then I take away the voltage and then I bring back the voltage, then I get also again peaks of the starting current or the restarting current for the motor. So we have to avoid that this function is active also in that state. Again, therefore we have the slowdown state to go away very fast from the running state in case of such a dynamic switchover. Okay, but that's just as a repetition apart. Yeah, the settings, very simple. It's an overcurrent protection. Here I choose 2 times nominal current. This depends really highly on the situation. What is the maximum expected current compared to the normal load current here? And here you can adapt. Another idea could be to find out what is the breakdown current. If the breakdown current, that means the current which I see before the motor comes to standstill, if the load becomes too big. If I'm above the breakdown current, I will slow down to 0, so I can shortcut this and switch off the motor in such a case. Okay, then yeah, we have a threshold for warning, threshold for operate. So the operate threshold normally is higher than this for the warning. Again, this depends what is driven by the motor. So you have to look here, what are reasonable settings for that. This does not really come out of the motor data because it's a protection of the connected machine. Yeah, this is what I already said. We have to see what are the expected normal load currents and what are the tolerable maximum currents here. Good, so this was it. Basically, what we consider the main important functions for the motor protection. What we did not talk about is that we have sensors and we can then detect the temperature of the bearing or of the stator winding. Basically, we have here also the possibility to add some definite time stages with different thresholds, so a warning and a tripping stage, depending what is the maximum allowed temperature there, for example in the bearing. And what we did not talk about is the under voltage protection. So this depends what is the maximum voltage drop you expect or what is possible for the motor still to start up. So if you drop below that voltage, you want to start a motor, this will not end good. So therefore, or end well. So therefore, then you can use the under voltage function to shortcut this process. Then you save also the heating up of the rotor of the motor unnecessarily. Okay, finally, I would like to talk a little bit about some additional functions and tools that help make easier the life. First of all, with a startup recorder, this records the startup phase of the motor. We can record currents, voltages, power, so analog values. We can also record binary signals like the circuit breaker close command, the status of the motor. It is a function which we have as a standard function built in all SIPROTEC 5 relays. And this is the slow scan recorder, which we took over from our fault recorder, the 7KE85. So this device has already all these recording functions, and in the SIPROTEC 5 protection relays, we took over a kind of fault recording or recorder light. So we have built in all these recorders, and one of these is the slow scan recorder, which we use for the startup recorder of the motor. Okay, so this can be displayed, this record, since this is a simple standard COMTRADE format, so very compatible, can be displayed with a standard SIGRA of the Dixie 5 software. It can be shown with a SIPROTEC with a Siemens COMTRADE viewer, with a SIPROTEC 5 Web UI, or any other COMTRADE viewer. So here's an example how this can look like in the SIGRA, for example. So we have here the voltages, 2 of 3 voltages, because my screen was not big enough. So the first is missing, of course. We have all 3 phase voltages, then the currents here. And then I put here some binary signals to show also this. And you see here I have the states. What is the purpose of such a starting record? The purpose is that I can verify the most important parameters during the startup, like the currents, like the starting time, the voltage which I see. And I can see over the time, if I make a comparison, if there has been changing something over this time. Yeah? If the voltage drop is now stronger, if I have a longer startup. So this could be all indication that something slowly gets worse in the motor, in the system. So I can verify changes in the behavior. And that's possible because I can store hundreds of these motor start records in the SIPROTEC 5 relays, because we sample just, we have no samples in these records, but we have measurement values. And depending on the sampling frequency for these measurement values, if you take just 1 cycle or 5 cycle, which is something like 100 milliseconds or longer, depending on this, you can store more or less records here. So generally you see numbers like hundreds if you go into the Dixie when you make the settings for this slow scan. That means over a relatively long time you can see if there are changes coming from the past. Okay, here we have the settings. We have a maximum record time. Good. Then the pre-trigger time in seconds, the post-trigger time in minutes, because it comes from this slow scan record, and here normally the time scale is minutes and not seconds, like in a fault record for the protection. And then we just decided to add 1 digit, so 0.1 means 6 seconds. Now it depends on what you trigger. If you trigger on the close command, then you need to set this post-trigger time as long as your longest startup time of the motor is. So how long you want to see this the data. You can also use, for example, the motor state starting. Then this will be active until the start has finished. Then you can choose the smallest post-trigger time, because then it's kept alive, the triggering, until the state goes to the running state of the motor, for example. Okay, here we see the averaging time. So this is the number of cycles. If I set 5 cycles, that means every 100 milliseconds I create a measurement value of the past 100 milliseconds, so the RMS value, what I measure there. And this is stored, and this is what we see here in our record. So you see this is like RMS values, and in that case, yeah, the cycle time I put 100 milliseconds. Good. The standard assignment that comes already with the application template for the motor protection is this here. So we added the state of the motor, then the currents and voltages if existent, and the close command. So consider this as the base configuration. If you want more signals in, then feel free just to add signals here in our information routing matrix in the Dixie 5. Again, this is freely assignable here. Okay, another tool which I would like to present you is the SIPROTEC Web UI. Yeah, this is a built-in web server in all our SIPROTEC 5 protection relays. And yeah, we see a picture here on the screen. So what you see here on the screen basically comes from the protection relay. Therefore, it's always there where you have a protection relay. The only thing what you need is a standard browser like Google Chrome or the Firefox or others maybe. And you access the relay via either the USB interface or via any Ethernet interface like the Dixie basically. Key features are standard web browser, so you don't need to buy a software. It's always there where the relays are, so it's a fine thing. You don't need to have a special software or something to work with a relay. All these tools I now present, we thought to consider as an add-on to the Dixie. Basically, the Dixie is the engineering tool to do everything, also the engineering between various relays. If you think about communication between the relays, Goose communication. This Web UI is a tool that you go to the relay and get some data, make some changes, work directly with the relay. So you cannot connect to, you can connect to more relays, but it's not that you make an engineering with that. It's more like an extended use of the display. So what you can do on the display, you roughly can also do here on the PC. More you can do here and in a more convenient way than on this display with a few keys what you have. Okay, what can we do? Status of the relay logs, spontaneous indications we can get. We can get fault records, statistic data, and more stuff. I think I have some examples here. I can visualize and modify active settings. I have a diagnosis overview with the overview of inactive functions, so it always makes sense to have a last look in there to ensure that all functions you want to have are really active, are switched on, are not blocked by any reason. So it's a good overview like that. The connection is via an encrypted way based on certificates, on the certificate that is in the relay. It's an HTTPS protocol, and you can use either a connection password or even role-based access control principle as we can use it in the Dixie 5. Or you quick and dirty, you have the relay just standing beside you, you want to quickly see something and this relay has no relevance in the substation, then you can also go there without any password, of course, but then it's not an HTTPS protocol, so it's not secured, not encrypted. This is what I normally do because I work with the relays not in the substations, but I want to find out some topics, some questions, and then I don't need that. But it's available. Okay, let's have a look. So this is basically the overview, and with each version we add a couple of functions normally, with each new version, firmware version of the relay. We can show, for example, a display screen with a dynamic indication of the breaker and switches. I can also put here an alarm list and also acknowledge this alarm list. So if it's red, I have to go there, then it goes away, for example. Here are settings, so I can change settings, and And then clicking here on this button, then I can download these settings into the relay, all without Dixie. I can show measurement values. If we talk about the first harmonics, the fundamentals, then I have here also a phasor diagram of the currents and voltages, and also here of the components, so negative, positive, zero sequence component of the currents and of the voltages, which then can be also shown here. Then the fault records, I can get fault records from the relay and store them on the local PC. I can trigger a fault record, and of course I can show the fault records here, again as you see here as an example. However, this is just, since this is coming from the relay, it's a limited way of analyzing the fault record. So all the nice features we have in the SIGRA, like circle diagrams, harmonics and so on, we don't have here really. Okay, so that's the web UI. One important point is also customer support. So there's a button support. If you have some issues with a relay, some questions, you can collect all the relevant data in one file and send it then to the customer support, so they get everything at once. So you save time instead of sending something there and then they ask back, we need this and this and this. So you have everything in one file and you can send it. I think this is also a very handy solution what we have. Then we have the next program. This is just called SIPROTEC Tools because it's a couple of functions which are in these tools here. I presented this a little bit more in detail in the first webinar. So if you're interested, go there please and have a look there, or we find also additional information on our internet homepage. So it's a toolbox for field tasks, which is helpful also if you mount the relays in the cubicle. So we have a hardware and wiring test of the relay. It's a portable, relatively small program, so you don't need to install it. It's just you start it, and you don't need a Dixie for that. So it's again decoupled, completely free of Dixie, and it's free of charge. So it's also an add-on, but for the nature of the function, it's a program on the PC compared to what we have built in the relays as a web UI. So we have here a little bit overlapping, but again, a little bit different applications of all these programs. Good. Hardware and wiring test. Let me see. No, I don't have more slides for that. Hardware and wiring test. That means in the cubicle, you can put a voltage on the cubicle terminals and then see if a binary input is activated, or you can close a contact in the relay and then verify if you go to the terminals of the cubicle, if really then you have a closed loop, so a short circuit, that the contact really closes the two terminals, which it should close on the cubicle, in the cubicle. Then you can upload a configuration someone gets from the Dixie. So the Dixie creates a so-called TCF file, and this file you can then take and upload this with the SIPROTEC tools into the relay. What else? Upgrade device functionality. That means if you need more function points in the relay, just take this tool, get the file, it's a so-called DAF, ending DAF file, from the function point manager, for example. There you can create easily such a file with additional function points, and then you take that file and load it into the Dixie the SIPROTEC 5 relays. A very fast process. So we have here a very high flexibility to adapt, let's say, the functionality of the relay. If you think about this with the function points, if you make a configuration for an end customer, maybe at the beginning it's not really clear how many function points you need, how many functionality, then it makes sense to buy the relay just without function points, make the complete configuration, discuss it with the end customer if you are a, how to say that, the supplier for the end customer. And then if everything is agreed, then you buy exactly the function points for your application, and you get this file in a couple of minutes. The time is the typing time you need to identify the relay, basically. The rest is very fast. And then you don't download it into the relay. Good. The same firmware, you can upload a firmware into the relay. Firmware and configuration you can upload to a big amount of relays at the same time. So this is a very fast uploading into the relay, even faster than with a Dixie 5, I would say. And finally, you can download device data from the relay to your PC, like fault records, like the configuration, other process data. Okay, and then we have the SIPROTEC Digital Twin. It's a virtual testing platform for SIPROTEC 5 protection devices. It looks like that if you start the program. You see here the relay. And this relay is created by the product code you create with a Dixie 5, then you export a simulation file. The simulation file is loaded into this in this application, into the digital twin, and then the relay starts up. You start up this and then you see the relay. What can you do? You have a hardware-free testing of your applications, of your configurations. You can test everything already before you have the relay or before you have the wiring of the relay together with other relays. Just to mention a few functions, basically it's all what we have in the real SIPROTEC 5 relays. So you can test a protection interface between two line diff protection relays. You can test goose signals coming from one relay to the other relay. In that case, you activate several relays, as many as you need, and then you can test the goose signal. So if a signal that is created in one relay arrives at the other relay, that this configuration is fine. You can test interlockings, the controls of all the switching elements you have, if this is working, if the interlocking is working, so you can go there and switch every switching element and verify if it's interlocked in all the conditions you want. In the same way, if you use our function for a on-load tap changer, a voltage regulation function, maybe even for parallel transformers, so also there we have a goose connection between various relays. You can test that stuff. If you have CFC logics in the relay, you can create the CFC logic and then make an online simulation with the CFC logic. So all this is possible with this digital twin to test beforehand, before you have even the relay on your table. Good. So you can replay fault records. So you have a fault record, maybe interesting for the end user, and you have a behavior of the relay which looks strange. Then you can replay the fault record on the digital twin and you can examine what's going on here. You can add additional signals, replay it again to get more information, change parameters, and then see if the behavior is better. Just to mention a couple of applications for this replaying of fault records. Okay, finally, I would like to mention that we have more information for you. We wrote a motor protection application guide, which you can download here under this link if you get the documentation. So it's a booklet which has approximately 80 pages. You see there is much more information that I could convey to you now in this webinar here. We have general information about protection functions. We have examples for various motor sizes, typical setting examples, also based on real motor data. So it's a good basis or source of additional information if you want to continue with motor protection. Okay, now it's time to go to the Q&A session. I would like to thank you for watching and listening to my explanation in this webinar. Thank you very much.
Okay, Klaus, now we've reached the end. And this has been almost, yes, but it's been a relatively long time, and there's been a lot that you've talked about today.
Yeah.
We have a few more interesting questions I'd like to go into. about this last session. First of all, from MRC, we got the following question. Do you have any predefined input data for motor manufacturers that can lead us to collect all of the necessary data at once? And are there any safe estimates for missing information?
I saw that this question got a lot of clapping hands after the question in the chat, so it seems that this is really a big interest. I think basically it's the stuff I presented, the settings and so on. You saw this example which I showed you as an example of settings coming from a motor manufacturer. I tried to condense that and write a list with the most important information you need from the motor manufacturer so that you can ask that. And maybe I provide it in an application note. I'm not sure which document it will be, but I think if there is such a big request, I will write something down so that you have something to hand over to the motor manufacturer. And if data is missing, I think this is a little bit a second part of the question. Let's say, for example, the K factor, there can be some tricks to get an estimate about that. I will also write down something like that. So how to get an estimate if something is missing. Better, of course, is to ask and get the data from the motor manufacturer, because then if it's an estimate and it's wrong, then maybe it's your responsibility. If you get the data from the motor manufacturer, you have sure data. So it's always better to get that data. But a few tricks I know I will write down as well somewhere.
Okay. Another question. In the last question phase, we asked for some feedback from PS. And we've gotten some information about that now. He said, I'm talking about the instantaneous stages, and you have second and third parameters. How must we use these parameters? Do you understand which functionality he's talking about?
I guess I'm not 100% sure, but I think it's about the overcurrent protection, these instantaneous stages. I showed how to make the short circuit protection for a motor. And the second and third parameter, the second is operate and fault record blocked. This is a general setting of all protection functions or all stages, more or less. You find them everywhere. This is basically if you don't want to trip on a function when a function has picked up, of course, but then also give the operate command. You don't want that this is treated as a tripping, but then in that case, if you say yes, operate and fault record blocked, yes, that means you will not give an operate signal, which then goes into a tripping signal at the end. But you have another signal, which is always there as an information operate delay expired. And this is then like a signal, a simple signal, basically. And fault record blocked means that in that case, there will be no fault record started on this action. So if you say no, which is the standard setting everywhere, then you will get this operate signal, which transforms to a tripping command in the function group circuit breaker. And you get also the fault record. And the third parameter is about inrush. If there's a transformer somewhere in between, so you have a transformer and then the motor, then you should consider inrush blocking. If you just have the motor, there's not really an inrush with second harmonic and that stuff that is typically for the transformer, then you don't need this inrush blocking. So I hope these are the two parameters you were aiming at. If not, please leave a comment again and explain which parameters you wanted to get explained again.
Okay, thank you. We hope that was what you were looking for to PS. And now TS asked the following. From the TIA portal by way of Profinet Profibles, can SIPROTEC configurations be done like that?
So SIPROTEC 5 relays can be configured mainly via the Dixie 5 and nothing else. We have an exception that is the web UI. Here can also change settings. Single settings, not all of them, like you can do from the front panel of the relay, but configure the relay from remote per default is not possible. Now there's maybe one topic where I don't know now. If you talk about settings for the communication, so which signals should be sent or something like that, I must admit I'm not the communication specialist. I will check that with our colleagues and then answer if there could be some possibility like that you can make a kind of standard configuration from remote.
Okay, we also got a question. You talked about SIPROTEC tools and Web UI, and they seem to be the same thing. When should you use each one?
Yeah, not really the same thing. If you figure it out, then you see that tools can be used during the installation for testing of the wiring, for example. You can use it also during the commissioning. You can, for example, download the firmware into the device, download the configuration into the device, upgrade the device functionality by downloading this dev file that contains the function points, for example. All that stuff the Web UI cannot do because the Web UI is built in each relay, in each SIPROTEC 5 relay. It's like a server for your web browser. What you can do with a Web UI, on the other hand, is so you can use this more during the commissioning and the normal operation. So this is more the focus. You can, for example, trigger a fault record and download a fault record, or download fault records in the relay without triggering. Also, that is possible, and save it on your PC. You can change single settings of the device. You can read out all kinds of logs which are in the device, and a lot of more stuff which I don't have the time to explain, not even in the webinar as such. But these are all actions you cannot do with a SIPROTEC tool. So it's really a subdivision of tasks. Maybe we have here and there some tiny overlapping, but basically it's two different topics.
Okay, but on a related note, Klaus, we also got the following question. You showed additional tools and functions. Are they included when I order the SIPROTEC 5 device, or do I have to order them separately?
So one tool is included. This is the Web UI, because the browser you have on your PC and this Web UI interface, or the surface, what you see on your PC comes from the relay. Therefore, it comes with a relay. The SIPROTEC Tools is a separate small program, portable program you can download from the internet, from our industry portal. It's free of charge, so it does not come automatically, but you can get it. Or if you install the Dixie, you get it also installed automatically from the Dixie. That's just a BiPAC, I don't know in
an
English.
additional feature.
Additional feature, yeah. And what else? The digital twin is separate. So it's a program, and you have to buy a license for that to use that, because it's extra effort and the extra feature what we have. So this does not come with a relay either.
Okay, there's one more question I think might be useful to bring now, Klaus. SZ asked about standard slow scan recorders, and if there's any inconvenience, any concerns about the trip record file, for example, in size.
So basically they are separated. In the settings, you reserve a certain amount of memory, and this is normally enough to host hundreds, I would say now, depending on the settings, but many of these slow scan records. And the idea of the slow scan record is, I don't know if it was really clear during the video, that you have only a few samples, so every 100 milliseconds, and then the size, you can register a long time first, so the full motor start, even if it's minutes, no problem. And the file size is relatively small, therefore you can host many of them. How this is internally organized with the memory, I'm not 100% sure. If we take away something from the standard recording, the fault recorders, if we have many fault recorders, or if we increase the memory for the fault recorders. On the other hand, the number of real fault records we can store in a relay is also high, so a maximum of 128. Or if you go into the manual, you see some examples how many fault records you can get. This depends also on the sampling frequency, but it's also a high number. So if it's not 128 because you have very long fault records, then maybe it's 50 or 60, but it's still enough, I would say, and there is not really an interference.
Okay, so what that basically means is we can be confident that the SIPROTEC 5 has enough capability to take on and store fault records and also scanning of startup sequences as what we would need for the operation.
Yeah,
Okay.
I think we can say that.
Anything else you'd like to say before we close, Klaus?
Not really.
Okay, you had a lot to say today, and we thank you very much for that. So first of all, we'd like to thank Klaus for the time and the effort he put in to prepare all of this to share it with us today. I'd also like to pass on from both of us our great thanks to all of you for your time and interest to be here with us today. We had about 150 participants through this entire period, learning about motor protection with SIPROTEC 5. This live session has been recorded, and it can be called up again for on-demand viewing later. Either you want to see it again or you want to share it with someone else who can call it up and also watch it. The only real difference is that you cannot pose questions during the on-demand viewing. So if you have any more questions that you're thinking of now, please put them in just now so that we can answer them in writing as we close off for this webinar series. You'll find in just a moment or two download files being made available here. It's the presentation that Klaus shared with us today, and also this motor protection application guide. Both of them can become very important resources with you when you start to plan new projects with motor protection requirements. And if you have any further questions and requirements related to motor protection or in SIPROTEC in general, please feel free to contact your local Siemens representatives for support wherever you happen to be. We know that we have had people from Zambia, South Africa, Angola, Mexico, and Korea in this webinar series. We're very happy about that. We thank you all for joining, not just those from the area managed from Austria, which we originally chose to do this webinar for, but really all of Europe and most of the world. It's great to see the interest. It's great to see the participation. We thank you all for your time.
Yeah, also thank you from my side. Have a good time.
Okay.
Stay safe.
And good day.